Okay, so thanks Adhip and others for organizing this and giving me this opportunity. It's a big title. I'll essentially illustrate all the words written here. So first of all, normal and anomalous transport. So what is Heisenberg chain? What is integrable system? And what is KPC scaling? Okay. So so this work is done with Manas, Abhishek, and Harvard. And this is going to be published in some finite time. And okay, so so okay, so my talk is like so okay, introduction and so how to study transport, scaling and approach. What is our approach to study this transport? What is KPC equation? What is KPC scaling? And what is the Hamiltonian we are interested in? And some results. Okay. So what is the question? Question is, so consider a system. So what can we say about its transport properties? So this is the question we want to ask, okay. So given a system, what is the transport properties? Transport of what? So for example, if you take a metal rod, so we can ask, what is how good it is, or I mean, what about the thermal conductivity or electrical conductivity? Or what is its transport properties? So this is the question we want to ask. So our usually so okay. So I mean, why thermal energy? Why electrical charge? So basically, we are interested in conserved quantities. So why conserved quantities? Because if the quantity is not conserved, then it's not so interesting. But if the quantity is conserved, we have very well-known equation of continuity, which we are like very familiar with. And here, let's say A is the conserved quantity and J is the current corresponding to that conserved quantity. Okay. So for a conserved quantity, for a system, we have this equation. So after that, what can I do? So the question is, so okay, so how to study transport in a generic system? One can do experiments, right? One can put thermal baths, one can put some perturbation, one can do experiment. So experimentally, and people have been doing experiments, and I mean, these are very old people, like Fourier-Ohm fix. So they got some, I mean, they have some empirical laws, and that gives us this diffusion equation or diffusive transport of quantities. For example, heat transport, electrical transport, whatever you take, usually it is diffusive. So why is it interesting? So the answer is known, right? So why are you interested in it? So okay, so these, so question is, so these kind of experiments are usually done in three-dimensional systems. Okay, so you take gas or take three-dimensional metallic rod or whatever. But I mean, thanks to experimental advances, we can perform these experiments on one-dimensional or two-dimensional systems. So what is one-dimensional system? So can you think of a one-dimensional system like just atoms, one line of atoms sitting? That's pretty. I mean, that we can imagine, but that's pretty hard to make, right, experimentally. Or a 2D system. So people have done these experiments on, let's say, 2D layer of atoms. And people have seen some interesting behavior that that this transport is not diffusive at all. Okay. So for three-dimensional system, we have this normal or diffusion, but one-dimensional, two-dimensional systems. So in some systems we do not have diffusion. This is the point. This is the motivation of this whole study. Okay. So in the title you saw normal transport. Normal transport means diffusivity. And anomalous transport means non-diffusivity. It can be sub-diffusive, super-diffusive, ballistic. So what is it? I mean, let's say I take a rod and I put some energy in it. Okay, so I'm putting some energy. So I mean, I can write a space-time function like this, right? And it will decay. Or it can do something like this. After some time, it can go something like this, right? So this is how this small energy packet is diffusing over time. So this is T1, T2, T3, and this is space. Okay. So you see a lot of this kind of curves. Okay, so so scaling. What is scaling? So diffusion equation gives me this diffusive scaling. So this is the first equation we solve when we study like partial differential equation in physics, right? We have this diffusion equation and we have like this sweet delta function initial condition, and we get this solution. But we can write, if you look it carefully, you can write it like this, right? We can put root t here, and this is x by root t some function, right? Exponential function. So this is a Gaussian. So this is called the Gaussian scaling. So if so, my Fourier or Fick's law, this will give me this Gaussian scaling of this conserved quantity. So this is my axt. Okay, this is what I have shown here is axt. This is, I start with some delta function and it goes Gaussian and it variance increases with time, linear with time. So notice these two things. One is this exponent and one is this function, okay? So in general, when we do not have this diffusion, we can still write this kind of equation. Why? Because you will always see, generically you will always see this kind of behavior. And when we have this kind of behavior, we can write that kind of equation. And two quantities are emerging. One is the scaling function and then one is the scaling exponent. And depending on this exponent, we can describe whether the transport is subdiffusive. I mean, it is lower than diffusion. It is super diffusive. It means its transport is faster than diffusion. And one is ballistic, which is like the kind of fastest. And one can have super ballistic, but these are the three regimes. Okay. I mean, so super diffusion means this is falling slowly. This faster, if so subdivision means falling slowly, slower than diffusion, and ballistic means something is like running with exponent 1. Okay. Yeah. Yeah, so this is a question that what is, so given some system, given some quantity of interest, what is the exponent and what is the scaling function? We do not know this scaling function. Take it, let's say xyz, okay? Whatever, we do not know this function. For diffusion, we know that this is exponential something. But why is it exponential? Why not some other function, right? So we have to identify this exponent and the scaling function. This is the problem, okay? Yeah. Right. So for one conserved quantity, this is what we want to ask.
This alpha is going to be same for all conserved quantities?
Not necessarily. Not necessarily. Not necessarily. We will see in this work. Just it will be clear in 2 minutes. So okay. So so one approach was to do experiment. Okay. So what can we do theoretically? This is the question. So our approach is to use this Onsager regression hypothesis. So what is this hypothesis? So given a system in equilibrium, so what is equilibrium? So if I take any quantity and system is in equilibrium, so I have some fluctuation around mean, right? This is equilibrium. This is precisely equilibrium. And you'll see that given a generic system, in equilibrium, this quantity is fluctuating, but if sometimes there is some unusual fluctuation, for example, if you take this room, the gas at some equilibrium is almost like uniformly distributed. But for thermal, there are thermal fluctuations. Sometimes somewhere there is accumulation of gas, and then it will diffuse. Okay, it will diffuse, or what will, I mean, it will do something like this, but what is the behavior, diffusive or what? That is a question. So Onsager said that these unusual fluctuations decay, and we can put some kind of initial condition that will also decay by the same law. Okay. So we will use this. So how? Okay. So take one-dimensional Hamiltonian system. Why one dimension? As I said, in 3 dimension it is not interesting. We could study 2 dimension, but 1 dimension, there are many one-dimensional systems where we can see anomalous transport. So that's why we take 1D Hamiltonian system. Okay, so we want to study theoretically, and we love Hamiltonians, right? So, so okay, we want to study this quantity. So now there is a lot of things going on in this quantity. So this quantity gives us equilibrium fluctuation. So you can ask what is AXT and what is this average. So what do? We take some equilibrium system. So what do you mean equilibrium system? We give it some temperature. So how do I give a temperature to a system? We do Monte Carlo simulation and we pick up some configurations of some temperature T. These are initial configurations. And as I have Hamiltonian system, we run Hamiltonian dynamics, right? So that's how we get AXT. And that's how, and picking up various initial conditions, we can do this average. And this, we are picking various initial condition from a Monte Carlo simulation. That means from a Gibbs distribution essentially. Okay. So one aside is KPZ equation and scaling. So if so KPZ equation is very interesting equation. So we have some snowfall on some landscape. Okay. So snowfall, and you can ask how this surface grows, how does this fluctuation grows. So that governs by this equation. You can see it almost looks like a diffusion equation, right? Del T and del X squared. But there is some nonlinear term, there is some noise term. Okay. So we can go into details, but we do not have time. But the question is, this particular quantity goes as f-KPZ function. This is your question, right? What is f-KPZ function? F-KPZ actually looks like Gaussian, but it goes as, at large x, it goes as minus x to the power x cube. Okay. So it is not Gaussian. At tails, things are different. Okay. Okay. So what is the Hamiltonian, integrable Hamiltonian? So what does that mean, integrable Hamiltonian? Integrable Hamiltonian means we have many integrals of motion. It goes as like degrees of freedom or something like that. So some example is one body, two body classical problem, harmonic chain, Toda chain, and many others, but very small amount of systems. Okay. So given, write down some Hamiltonian blindly, and there is 99% chance that that will be non-integrable. Okay. So non-integrable Hamiltonian means there is a finite number of conserved quantities. Okay, so let's consider this classical x-axis spin chain, and this is non-integral system. Okay, so this is one like we study in StatMech. So these are classical spins. They are lying on unit sphere. Okay, and this is non-integrable. There are few conserved quantities, energy and magnetization, known conserved quantities. And so there's so j greater than 1 means easy axis, and j less than 1 means easy plane, and j equals to 1 means isotropic. So when j greater than 1, then spins are more tending to align near z axis, and z less than 1 means they tend to align on xy axis. So we take an integrable version of this. So this Hamiltonian looks terrible, but somehow this is integrable. Okay. So all the known conserved quantities are known. So we do simulation, and what happens? So we study these two quantities, energy and spin. You can ask, okay, integrable Hamiltonian, we have n number of conserved quantities, but okay, that sounds good, but to write down those n conserved quantities for some n degrees of freedom, that is a non-trivial task, and to study that is even on a much more harder task. So we take the spin and energy, which we know are conserved, to study it. We can see that in easy plane regime, the spin is ballistic. How do we do it? We take these exponents, right? T to the power 1 is ballistic. So what about energy? Energy is also ballistic. So what about easy axis regime? We see difference. We see spin is Gaussian. So suddenly it becomes Gaussian, right? We change the parameter in the Hamiltonian, spin transport becomes diffusive. That is strange. Okay, and what about energy? But energy remains ballistic. Why? That is also strange. So in isotropic regime, things become even more interesting. We can see this kind of curve, as I showed you. You will always see this kind of curve in these spatio-temporal correlations in most cases. And then, what is the exponent? You can see the exponent is 2/3. So again, it is very strange that at rho equals to 0 case, it is not ballistic, it's not diffusive, but it is super diffusive. So what is the scaling function? You can see it also fits with KPZ. So you can see there is a similarity between KPZ and Gaussian. You cannot distinguish so well. So now, if I put it in log scale,
Avijit, 30 seconds. Wrap up.
If we put it in log scale, things become different, and so we get KPZ scaling. This is very clear, right? We get KPZ scaling, and this is kind of a new result or main result of our work, that in an integrable system, besides getting various exponents, we also get KPZ physics. KPZ physics is emerging out of this integrable system. Okay. Okay, good. So how do I conclude? So we study this Adhip integrable spin chain. Here we get various kind of transport in various quantities in various parameter regimes. Very featureful model, and we also get KPZ at the end of the day. But okay, these are observations, and the theory mostly is unknown. Okay, thank you.
Questions, comments?
One question. Like, how does the notion of noise arise in transport? In the KPZ dynamics, we have that eta term, right?
Right.
But in the case of transport, how does that term arise?
Well, I mean, we are not writing equation for our case, but we can in the nonlinear fluctuating hydrodynamics formalism. So that in that formalism we put it by hand, and that is because of we are neglecting many degrees of freedom. We are taking average and stuff like that. That's not so well understood. I don't understand it very well.
More questions? If not, let's thank Avijit again.